Good afternoon, everyone. My name is Weiwei Chen. I work on the Mojo language team at Modular. Today, I'm going to talk about efficient data flow analysis on region-based control flow in MLIR. A little bit overview of what I'm going to talk today. I will first give a quick recap on what data flow analysis is. Then I'm going to talk about introduce this region-based control flow representation in MLIR that we're using in Mojo. And then zoom into a very specific data flow analysis, SCCP, which is Sparse Conditional Constant Propagation, and how can we implement in a very efficient way by using this new control flow representation. And at the end, we will have some discussion and questions time. So data flow analysis. Data flow analysis is the type of analysis that we get information that is propagated along following along the control flow graph of a program. It is a static analysis that have to cover all the edges that how data is flow in the program. The analysis states are very useful for some of the optimizations for compilers, such as sparse conditional constant propagation SCCP, like value range analysis, and a lot of other type of analyses. So typically, there are two types of data flow analysis. A sparse data flow analysis mostly is associated with SSA values. So all the analysis states is just one-to-one mapping to the SSA value. There's also another type of data flow analysis, is a dense analysis, where the analysis state has more context of the whole program, does not necessarily have to associate with SSA value. For example, you have a memory, and there's a store operation, you will update the memory. So you update like the state before the operation and the state after the operation. One of the very critical data structure that's being used in data flow analysis is lattice. So lattice usually has for data flow analysis, there's a bottom state, which is the uninitialized state. It's a default state. And there's a top state, which is the overdefined state, which means that there's not much useful information we can gather. So that's the kind of the most conservative state. And there can be states in between, which is defined by what type of the data flow analysis we're going to apply. There are two types of binary operations we can apply on the lattice elements. One is the join operation, one is the meet operation. If it's a lattice, the result of the meet join should always be a unique result. So this allows when we have multiple states, we can kind of reduce it into a single thing. That's why it is a very powerful tool to simplify like a combinatorial states. So lattice is pretty commonly used for data flow analysis. Of course, there's also other types of data structure can be used for data flow analysis. It can be a little bit more complex, but we are going to focus on lattice today. So data flow analysis has already exists in both LLVM and MLIR. In LLVM, there's SCCP, there's IP-SCCP, which is an inter-procedure version. Both of them use the SCCP solver, and there's also CLAN data flow framework. In MLIR, there's data code analysis, integer range analysis, and a bunch of analyses. And MLIR actually also has a extensible and composable data flow framework, which was presented last year at EuroLLVM, that you can actually build off the tree data flow analysis by using that framework. So basically just define what the lattice operation is, and then you can have your own type of, you can build your own type of data flow analysis. So both LLVM and MLIR perform the analysis follow a general representation of the control flow graph. So basically we have basic blocks, we have branch and conditional branch, and there's a fee node to collect the different branching targets. They can be a little bit complex because the general control flow graph does not necessarily reflect the logical meaning of the program. It's kind of more breakdown representation. It can be irreducible. And the fee node also introduces complexity. So for both of the two framework, the data flow analysis basically is a iterating through an analysis state solver to a fixed point. So sometimes this solver can be quite expensive to run. For example, there's a control flow graph here. We have a SCC in this graph, the strongly connected components, and there's a tail part here. So for a solver-based analysis, so the update order can be arbitrary because the solver does not really know, does not really care the order of the updates. So for this case, if we do the back edge, every time we do one back edge and the tail and another back edge and the tail, then the complexity is going to be quadratic. So it can be quite expensive. So how can we improve that? We want to first to have a better way to represent the control flow. So what we are trying to introduce, and this is already being used in Mojo language, is a region-based control flow representation in MLIR that can represent a structured control flow. It is pretty much like the MLIR SCF, the structured control flow dialect. However, in addition to that, it supports the early exits. So we can actually support break, semantics like break and continue in this representation. The reason why SCF does not support it, because this is kind of breaking, like violating the language reference of MLIR. Because in MLIR language reference, that only terminator operators can exit a basic block. So for an example here, we have this if that has a break. The break can exit the basic block of the if, but the if also has to exit the loop. But if is not a terminator operator. So we cannot have that. That's the reason why SCF does not support early exits. So what we're proposing here is a type of operations that is purely region-based. So we'll forget about the basic block restrictions. We just focus on the region-based representation. So that now we can support kind of like early exits of the loops. This representation will not support any arbitrary control flow. So when you exit the branch out of the region, it should always pop back to the parent region, which means that goto is not allowed because goto may go to any arbitrary destination. This is actually really nice because it can give us a structured representation of the control flow. It will give us a very close match to the high-level control flow from the program's logic, and it is very easy for front-end to emit directly. This is what we already use in Mojo, but we also have heard that this can benefit for things for MLR projects like Triton and Polygeist and so on. So what we're trying to propose here is not a dialect. It's more like a type of operations. Think about like interfaces of the operations to capture control flow. So by implementing these interfaces, we can have like a region control operations to represent like loop or if or for. We can have region terminators like yield, break, and continue. The interfaces will define the general abstraction of how the interface, how the branching interact with its parent, so that we have abstract definition of how the control will flow without having to special casing what exactly the operation is. And we can write general passes for any operations that's implementing this interface. Potentially, this type of operation can also coexist with the current control flow representation and MLIR SCF, as long as the control flow flows correctly in the region subtree. Okay, so with this representation, now let's look at a concrete example of data flow analysis, SCCP. So just a quick recap, sparse here means it's related with SSA, the lattice value is associated to SSA value. Conditional constant propagation basically is doing dead code elimination while doing constant propagation, or constant propagate while doing dead code elimination. So it will conditionally get rid of some of the branches if we have enough information. This is the type of the constant lattice that we use in SCCP. It has the bottom state and has the top state overdefined. And in between, there's only one level as the constant value that we may generate while doing the analysis. So any elements joining with the top will become the top. Any elements joining with the bottom will be any element itself. And in between, for any constant joining with another constant, if they're the same constant, then they stay as the same constant. If they're not, then they become overdefined. So it's a pretty simple lattice, only of height 2. For an example here, we have x equals 1, we know the lattice value becomes 1, y equals 2 becomes 2. And if we know that it has 2 regions, so we'll have to go to both of the regions here. And A on this branch is 2, on the fourth branch is also 2. At the end, we will have to join these 2 regions because they both belong to the if operation. Because 2 and 2 are the same, so the join result becomes 2. And now we know that this condition will never be true, so we can actually get rid of this branch. The loop is gone, and we can propagate the value, so we get b become 4. So this is pretty simple. How SCCP works. While we're propagating the constant, we will cut some of the branches. So here's an example when we have a while loop. A becomes 1, and we have the while. We know that the condition is true, so we go to the body region of the while loop. And we have if, so if has 2 regions. On the left side, A has assigned value of 3, but it has a break, so it will have to break back to the parent. It becomes the return value of this branch is 3. And on the right side, it's just incrementing the value of 2. So A becomes 2, and continue means that we have to go back. But we also know that input value of A is 1. So when they join together, it becomes overdefined. And if the value of A is overdefined, now it's possible that we can either go inside of the body or just go to the end of the loop. So go inside of the body will still be, on the left side, it will still be the same, but on the right side, A becomes overdefined. Now it converges, so it's just overdefined. And on the left side here is overdefined, and when we join overdefined join with 3, it becomes overdefined. Everything is overdefined. So kind of not very useful analysis here. But if we look at this loop, we can figure out that if we can exit this loop, the value of A will always be 3, right? Because if we break, the value is assigned by 3, or if the condition is not true, means that A is 3. So we can actually do this if we can simulate this loop. Because we have a structured representation which reflects directly to how the program works, so we logically know that, hey, this is a loop. Now we can put a context into, when we go inside of loop, we can kind of put a scoping on SSA values. Now when we try to merge on the right side, the 2, for the next iteration, we do not actually have to join with the value of the first iteration because it will never be the same. So we can just keep doing the scoped SSA value, kind of interpreting the loop in a way. Now we know that, hey, all the branches will all reach as the value of 3, and we join them, it becomes 3. Now the if actually, one of the if, the else region will never be reached. So we actually can have a more accurate result if we can do a kind of interpreting way of the loop. But because we have this structured representation of the loop, it is possible to do so. However, this can be a little bit dangerous because we can have a really long loop, or the loop can have very deep nestedness. So if we are trying to simulate a loop in this case, it's possible that it can explode compilation time. So we can do some trade-off, try to apply some heuristics to see whether we want to have more accurate result in trade-off compilation time. But with this representation, this is possible to make it happen. So now let's step back a little bit from the more higher level why this representation helps us to have a more efficient implementation of SCCP. So basically, a structured control flow representation will always give us a reducible control flow graph. A reducible control flow graph means that we have a graph that has SCCs in it, and all the SCCs should only have one single entry to the SCC. And in SCC, in this representation, basically they are loops. So because they only have one single entrance, you can sort of think of that the SCC can collapse, become one node, then everything becomes linear. So when we apply this analysis outside of SCC, it's just forward linear going forward. And within the SCC, the forward is still forward, and backhatch, we actually only need to do it twice because our lattice height is only 2. So in general, the complexity of this analysis the complexity will be kind of about twice of the operations in the code size. This also matches pretty well with the theoretical SCCP complexity, which is linear to the SSA edge and the control flow edges. So we can take a look at the previous example to compare it with the solver-based approach. So for the solver-based approach, because the update order is arbitrary, it's possible that we may run into a case that it's quadratic. But with this structured control flow in mind, now we can actually update the state, like try to converge the SCC first, and then run the tail. Now, actually, the complexity is linear. So the critical part is that with this representation, we can update the state in a more guided way and ordered way so that the complexity is reduced. Some experimental results, because these are the things that we care about. 3 big models, we can get about 0.6 to 1.2x speed up by having SCCP. It's not huge, but it's pretty stabilized because this is running on a pretty quiet environment and has been running multiple iterations for a specific set of time. And this is a statistical result in terms of performance gain. And we can also take a look at the compilation time. There's not a significant difference with or without SCCP. And actually, some of the runs that SCCP is even faster because we are getting rid of more code. So you're compiling less code and less faster compilation time. So conclusions. What we introduced is a structured region-based control flow representation that is pretty similar as MLIR SCF. But it also allows early exits so that it can give us a reducible control flow that can guarantee almost the best case complexity for data flow analysis. It is actually logically pretty easy to debug because it has a very close match to the higher level programming language. And it's actually generally applicable not just to SCCP, but also to other type of analysis, as long as you just define the meaning of the letters. We are planning to upstream. Mojo compiler is not fully open source yet, but we are planning to upstream this representation. There's already a discussion in the MLIR workshop that the community is also very excited and has very positive feedback on this representation. So we will work with the community to upstream it. There's already an RFC out there. So hopefully that once this representation is upstreamed, we can first get first-class support for successors and predecessors and other type of analysis utilities so that we don't have to write these things in our compiler specifically. And once the representation is upstreamed, we can also start to upstream the data flow analysis that we have been built based on this representation. This is pretty much it. So I'm wondering if there's any questions.